In high latitude regions, low temperatures cause a permanent ice cover on the sea surface. This will affect the deep circulation as well as the surface circulation that we're learning about. So the high latitude regions includes the Arctic and the Arctic Ocean, which is frozen with sea ice in this image, and the Antarctic, which has glaciers or ice that is formed over the continent, as well as some sea ice surrounding the continent. So what I want to point out first is that sea ice, which you see here, slabs of sea ice with the polar bear sitting on top, is different than icebergs. Okay, icebergs, they break off from glaciers which have originated on land. So glaciers originate on land, and if they break off, they form icebergs that float on the ocean. Now, the sea ice forms directly from seawater. And as I said before, sea ice is found in Antarctica and in the Arctic Ocean, as well as in extreme latitude regions of the North Atlantic Ocean. So the North Atlantic Ocean borders here. This is Greenland. So you can also find sea ice in the North Atlantic Ocean as well. So the difference between sea ice and icebergs, sea ice forms from the freezing of the seawater, and icebergs are chunks of ice that break off from a glacier. Glaciers are formed on land. So here I have an image of Pine Island Glacier and a huge iceberg, a flat iceberg that has broken off from this glacier, and it's now going to drift in the ocean. So the sea ice forms directly from water in the process that I will describe here. Because of the salt content, the seawater begins to freeze at about minus 1.8 degrees Celsius, a lower temperature than that of fresh water, and a property that we call the freezing point depression, which we studied in the previous module. The ice formation begins at the surface with the formation of small needle-like ice crystals called frazel. These will accumulate and make the water appear slushy and cloudy. This stage is referred to as grease ice, so that's figure A. In grease ice, small needle-like hexagonal six-sided crystals eventually become so numerous that this partially frozen, partially liquid slush develops. The slush then begins to form a thin sheet, and in calm locations, a calm surface layer is developed in the named nihilus. So that's figure B. These can then break off by wind stress and wave action into disc-shaped pieces called pancake ice. So that's image C. That's an image of pancake ice. As further freezing occurs, these pancakes can merge to form larger ice flows. So that's figure D. And over time, the ice flows merge and create large sheets of ice, which are moved by winds and currents to produce the pressure ridges along their margins. So that's the next picture. So here we have the pressure ridges that form with the colliding ice sheets. Conditions that promote sea ice formation, the calm water conditions that enable the pancake ice formation, and temperatures below minus 30 degrees Celsius. The sea ice formation is a self-perpetuating process. It feeds itself. And that's because the salt and other dissolved components in the seawater will remain in the water as the water freezes. So as the sea ice forms, the salt of the seawater and other dissolved components will remain in the surrounding water. This will cause the salinity of the surrounding water to increase, and will add solutes, other dissolved compounds, to the water surrounding the sea ice. Now recall the freezing point depression property of seawater. If solutes are added to the water, it lowers the freezing temperature. Also, the salt that stays in the surrounding water that did not freeze in the ice will make that water more dense. So this saltier dense water will sink and will be replaced by water with lower solute, lower salinity, and lower density content. So this water that replaces will freeze more readily than the high salinity water. And thereby it establishes a circulation pattern that enhances the sea ice formation. Okay, so if I ever ask you what happens to the salt in the seawater as sea ice forms, well, the salt is expelled into the surrounding water. The salt does not freezes in the ice. And so that creates a dense layer of water surrounding the seawater, the sea ice. And so that layer will sink because it's more dense. And it's going to be replaced by a less dense layer with which is more readily available for freezing and formation of sea ice. So that's the circulation that enables the formation of sea ice. And one last note about sea ice is that the recent satellite image analysis of the extent of the Arctic Ocean sea ice shows that it has decreased dramatically in the past few decades. This accelerated melting appears to be linked to shifts in the northern hemisphere atmospheric circulation patterns that have caused the region to experience anomalous warming. This is a still image visualizing the Arctic sea ice on September 16, 2021, when the sea ice appeared to reach its yearly minimum extent. So this is the sea ice minimum extent in September 2021, 4.72 million kilometers squared. The yellow line shows the average minimum from the time from 1981 to 2010. So a 30-year average of the sea ice extent represented by the yellow line and the minimum extent at a particular year. So it's comparing an average to a current year. And as you can see that that data point here for 2021 will is much different than the average. So that's what we called an anomaly, when the measurement is significantly different than the average. Um, we call that an anomaly. So the extent of the Arctic Ocean during during September. So you have to consider that the stations, the seasons of the year, is much lower than an average minimum for the 30-year data series from 81 to 2010.